Picture a single particle, a tiny speck of existence, facing a solid wall it simply should not be able to cross. By all the rules of the universe as we know them, this particle is trapped. It lacks the energy, the brute force, to break through this fundamental barrier, and yet, in a fleeting instant that defies logic, it vanishes from one side and instantaneously reappears on the other. It didn't go over the wall, it didn't go around it. It performed a cosmic magic trick, tunneling straight through the impossible. This is not science fiction. This is quantum tunneling, a real and verified quirk of our reality that operates on a scale so infinitesimally small we can barely conceive of it. But today, we are going to ask a question that stretches this tiny event across the entire expanse of existence. Could this same quantum quirk, this momentary blink of a particle, be the hidden trigger for events so colossal they reshape the cosmos itself? We often think of the universe in terms of cause and effect on a grand scale. Stars explode, galaxies collide, and these titanic events seem to be the sole architects of cosmic change. But what if the true architects are working in the shadows on a level far beyond our everyday perception? The world of quantum mechanics is a realm of probability and potential, where the normal rules of physics take a holiday and the impossible becomes not just possible but routine. In this hidden domain, quantum tunneling is one of the most common yet most baffling phenomena. It's the reason our sun shines, allowing protons to overcome their mutual repulsion and fuse together, giving us light and life. It's a fundamental process woven into the fabric of reality at the very smallest scales. But what if its influence doesn't end there? This journey we are about to take together is not just about understanding a strange scientific principle. It is an exploration into the very heart of how our universe might truly operate, connecting the unimaginably small to the incomprehensibly large. We are going to venture into theories that suggest quantum tunneling could be behind some of the most dramatic and universe-wide events imaginable, from the spontaneous birth of new universes to cosmic catastrophes that rewrite the laws of physics. We will explore the idea that our entire reality might be perched on a knife's edge, maintained by a delicate balance that a single, random quantum tunnel could shatter. So prepare to have your perspective stretched. We are about to dive deep into the wildest implications of a quantum quirk and discover how the smallest things in existence might hold the greatest power over everything we know. To grasp how something so small could have universe-shaking consequences, we first need to get comfortable with the bizarre rules of the quantum world. Let's start with a thought experiment from our everyday classical reality. Imagine you're rolling a ball up a hill. If you give the ball just enough energy, it will roll up to the very top of the hill, hesitate for a moment, and then roll back down to you. If you don't give it enough energy, it won't even make it to the top. It will simply roll back down before reaching the summit. This makes perfect sense to us. The hill is a barrier, and the ball needs sufficient energy to overcome it. In physics, we call that hill a potential barrier. Now, let's shrink this scenario down to the quantum level. Instead of a ball, we have a single particle like an electron, and instead of a hill, it's facing its own version of a barrier, perhaps a strong electrical force or a region of space it seemingly shouldn't be able to cross. According to the classical rules, if the particle doesn't have enough energy, it should just bounce back, just like our ball. But the quantum world doesn't play by those rules. Here, particles don't just behave like tiny billiard balls, they also have wave-like properties. This is a crucial point. We describe this wave-like nature with something called a wave function, which essentially represents the probability of finding the particle in a particular place. Think of this wave function not as a solid object, but as a ghostly haze or a cloud of possibility surrounding the particle's location. This probability cloud doesn't just stop abruptly at a barrier the way a ball would. Instead, it decays exponentially, fading away but never quite reaching zero on the other side. This means there is a very small but real probability that the particle is already on the far side of the barrier. It's as if the particle's possible locations include a tiny, faint shadow of itself existing beyond the wall. When we actually detect the particle, this probability collapses, and we find that the particle has, in effect, appeared on the other side without ever having possessed the energy to go over the top. It didn't break through, it tunneled through. This is why the analogy of a person walking through a wall is so often used, but it's vital to understand the numbers involved. For you or me to quantum tunnel through a solid wall, the probability is so astronomically, incomprehensibly small that you would have to throw yourself at the wall for a period of time longer than the current age of the universe, and even then, it's almost certainly not going to happen. The probability drops off dramatically with the mass of the object and the thickness of the barrier. This is why we don't see people accidentally phasing through chairs. But for something as tiny and lightweight as an electron facing a barrier that's only a nanometer thick, tunneling isn't just a theoretical oddity, it's a commonplace event. It's the reason scanning tunneling microscopes can image individual atoms and why the electronics in your phone work. This probabilistic tunneling is a fundamental feature of our universe, a direct result of the fuzzy, wave-like nature of reality at its smallest scales. So what is the actual mechanism that allows a particle to perform this seeming magic? The key lies in one of the most fundamental and, frankly, spooky principles of quantum mechanics, the Heisenberg Uncertainty principle. This principle states a profound truth about our universe. There is a fundamental limit to how precisely we can know certain pairs of a particle's properties at the same time. The most famous pair is position and momentum. You might think you could, with perfect equipment, measure exactly where a particle is and exactly how fast it's moving. But the universe itself forbids this. The more precisely you pin down its location, the less you can know about its momentum, and vice versa. There is always an inherent fuzziness, a built-in uncertainty. This isn't a limitation of our measuring tools, it's a property of reality itself. Think of it not as a blurry photograph, but as if the particle is intrinsically smeared across a range of possibilities. This uncertainty creates a tiny but crucial loophole in the face of an energy barrier. For that brief instant when a particle interacts with a barrier, the uncertainty in its energy opens a window. The principle implies that energy can be borrowed from the vacuum of space itself, but it must be paid back incredibly quickly. The thicker or higher the barrier, the faster this energy debt must be settled. This fleeting fluctuation can provide just enough of a boost for the particle to, in a sense, sneak through the barrier. It's as if the universe, at its most fundamental level, operates with a little bit of creative accounting, allowing for transactions that would be impossible in our classical macro-scale world. Now, let's connect this to the wave function we mentioned earlier, that cloud of probability. When this probability wave encounters a barrier, it doesn't just hit it and stop like a water wave hitting a seawall. Instead, it behaves more like a sound wave passing through a thick door. It doesn't stop instantly, but its intensity fades the further it goes into the barrier. Mathematically, we say it decays exponentially. This means the wave function doesn't drop to zero the moment it touches the barrier. It continues inside the barrier, getting exponentially weaker with every atom's width it penetrates. If the barrier is thin enough, there's a chance, however small, that the wave function hasn't completely faded away by the time it reaches the other side. That tiny, non-zero value on the far side represents the probability that the particle will be found there. The act of measurement then collapses this fading wave of possibility into a definite reality, and we detect the particle as having tunneled through. To visualize this, imagine you're in a dark room with a very thick felt curtain separating you from another room. If you shout, the sound wave will be almost entirely absorbed by the curtain. Someone on the other side won't hear you. But if that curtain were replaced with a sheer silk scarf, some of the sound wave would make it through, attenuated but still audible. the quantum world is even stranger. It's as if you're shouting at a solid brick wall, and because of the wave-like nature of sound and the uncertainty inherent at that scale, there's a vanishingly small but real chance that your shout could manifest as a whisper on the other side without ever having physically traveled through the bricks. This exponential decay is the reason why tunneling is a common event for light particles and thin barriers, but becomes unimaginably rare for larger objects. The probability isn't just small, it plummets at a staggering rate as the barrier gets wider or the object gets more massive, which is why we are securely anchored in our chairs and not randomly tunneling through the floor. Understanding this strange quantum behavior is one thing, but truly appreciating its power comes from seeing it in action, not in a textbook but in the world around us and far beyond. It powers the devices in our pockets and lights up the heavens above. Let's start with the technological marvels that depend on this quantum quirk. You are almost certainly using quantum tunneling right now as you watch this video. The flash memory in your phone, your computer, and your USB drives relies on it. In a flash memory chip, tiny cells store bits of information as electrical charge. To program or erase these cells, electrons need to be moved across a very thin insulating barrier, an operation that would require a large and damaging voltage if done classically. But because the barrier is so incredibly thin, electrons can tunnel right through it. This allows for fast, efficient, and low-power writing and erasing of data, making our modern, portable digital world possible. Another critical component is the tunnel diode, a semiconductor device with a unique property. Unlike regular diodes that block current until a certain voltage is reached, a tunnel diode exploits quantum tunneling to allow current to flow at very low voltages. Then it actually decreases current as voltage increases, a very non-classical behavior before increasing again. This negative resistance effect makes them incredibly fast, capable of switching on and off at frequencies far beyond the reach of ordinary transistors. They became vital in early high-speed computing and remain important in specialized applications like oscillators and amplifier circuits, especially where extreme speed and low noise are critical. These are not obscure laboratory curiosities. They are workhorse components that demonstrate how we have harnessed the probabilistic nature of the quantum world to build practical, reliable technology. Now, let's zoom out from our gadgets to a scale that is almost impossible to comprehend. The heart of a star, our sun, and every other star like it, is a colossal nuclear furnace, fusing hydrogen atoms into helium and releasing the energy that makes life on Earth possible. But there's a seemingly insurmountable problem at the core of this process. Protons, the nuclei of hydrogen atoms, are all positively charged, and as we know, like charges repel each other with an immense force called the Coulomb barrier. To overcome this repulsion and get close enough for the strong nuclear force to pull them together into fusion, the protons in the sun's core would need to be moving at speeds and temperatures far higher than what actually exists there. Based on classical physics alone, the sun should not shine. It doesn't have the classical energy to ignite. This is where quantum tunneling saves the day and quite literally allows our universe to be filled with light. The protons in the sun's core don't have the energy to go over the Coulomb barrier. Instead, they tunnel through it. The probability for any single pair of protons to tunnel is vanishingly small. But the sun is an unimaginably vast reactor. In its core, there are so many protons colliding with each other so frequently that these incredibly rare tunneling events become not just possible but constant. Every second, countless protons defy the classical rules and tunnel just close enough to fuse, releasing the energy that has sustained our planet for billions of years. So, the very warmth you feel on your skin on a sunny day is a direct result of a quantum tunneling event that occurred 150 million kilometers away. This is the profound bridge between the microscopic and the macroscopic, A subatomic probability, amplified by cosmic scales, becomes the driving force behind the largest engines in the galaxy. So we've seen how quantum tunneling is essential for the technology in our hands and the stars in our sky. But this quantum quirk might have a much darker, more profound role to play, one that extends to the ultimate fate of everything that exists. To understand this, we need to shift our perspective from particles and stars to the very fabric of spacetime itself. This brings us to one of the most dramatic and unsettling hypotheses in all of theoretical physics: the idea that a single, random quantum tunnel could be the cosmic trigger for the end of our universe. The key to this mind-bending concept lies not in a particle but in a field. You've likely heard of the Higgs field. It's an invisible energy field that permeates every corner of the universe, and its interaction with particles is what gives them their mass. Think of it like a cosmic molasses. Particles moving through it experience a kind of drag, and that resistance is what we perceive as mass. Without the Higgs field, electrons would zip around at the speed of light and atoms could never form. So this field is absolutely fundamental to the structure of our reality as we know it. Now, the state of this field, its current energy level, is what physicists call our vacuum state. It's the lowest energy configuration we currently observe, the background hum of the cosmos. But here's the critical question: is this truly the lowest possible energy state? Or is our universe merely sitting in a comfortable but temporary valley on a much larger cosmic landscape? This is the premise of the false vacuum theory. Imagine our universe is like a ball resting in a small depression on the side of a vast, sloping mountain. The ball is stable for now. It would take a significant nudge to push it out of that little hollow. This hollow represents our false vacuum, a metastable state. It seems stable, and for all intents and purposes, it has been stable for nearly 14 billion years. But it's not the absolute bottom. Somewhere far below, there is a much deeper valley, a state of true vacuum where the Higgs field would have a fundamentally different value. In that true vacuum state, the properties of the universe could be unrecognizable. The laws of physics themselves, the constants that dictate how particles interact, the strength of forces, the very nature of mass and energy, could be completely altered. This is where quantum tunneling enters the picture with catastrophic potential. How does our universe get from this seemingly stable false vacuum state down to the true vacuum? It can't just roll there classically. There's a giant energy hill separating the two states. But just like an electron facing a barrier it can't classically cross, the universe itself could, in theory, quantum tunnel through that energy barrier. A tiny, random quantum fluctuation in the Higgs field, a bubble of true vacuum, could spontaneously form somewhere in space. The probability of this happening in any given cubic centimeter of space in any given second is astronomically, mind-numbingly small. But the universe is vast, old, and filled with cubic centimeters. Given enough time and enough space, the improbable can become inevitable. If such a bubble were to nucleate, the consequences would be beyond any catastrophe we can conceive. The laws of physics inside this bubble would be different. This new vacuum state would be stable and it would expand, not like an explosion but at the speed of light. The wall of this bubble would be a wave of fundamental change, rewriting the fabric of reality as it passes. As it expands, it would release a colossal amount of energy, the energy difference between the false and true vacuum states. But this isn't an energy that would create new stars or galaxies. It would be an energy that annihilates the old ones. Every atom, every force, every structure in the universe would be fundamentally altered in an instant. The wave would be completely undetectable until it arrived. Since it moves at light speed, there would be no warning. One moment, the universe exists as we know it. The next, everything is gone, replaced by a new reality with potentially different and perhaps inhospitable physical laws. This event wouldn't just destroy Earth or our galaxy. It would be a universe-wide reset button, triggered by a single, random quantum event on a scale smaller than an atom. This concept of a universe-ending bubble born from a quantum fluctuation is perhaps the most chilling and final scenario physics can offer. Let's try to visualize this event, this bubble of doom, as it would unfold. Imagine a point in the emptiness of intergalactic space, far from any star or planet. At this location, through the same probabilistic tunneling mechanism that lets an electron through a barrier, the Higgs field experiences a rare fluctuation so profound that it quantum tunnels through the energy mountain, separating our false vacuum from the true vacuum. In that instant, a microscopic sphere of the new reality pops into existence. This is not a bubble of air, it is a bubble of redefined physics, a sphere where the Higgs field has settled into its true, lowest energy state. The moment this bubble nucleates, the rules change inside it. The fundamental constants that govern our universe, the strength of gravity, the electromagnetic force, the very nature of mass itself, would be instantly and permanently altered. The laws of physics as we know them would cease to exist within this region. Matter as we understand it, built upon the specific constants of our vacuum, would be fundamentally incompatible with this new state. Atoms could not hold together. Protons and electrons might instantly decay into new forms of energy or different, exotic particles. The very building blocks of reality would dissolve, not in an explosion of fire and light, but in a silent, fundamental rewriting of the cosmic code. Everything inside the bubble is immediately and irretrievably erased from existence as we define it. But the true horror lies in what happens next. This bubble of true vacuum is stable, and it is surrounded by the unstable, higher energy false vacuum of our universe. Nature abhors an energy gradient, and this new state will immediately begin to expand. The boundary of the bubble, its wall, is a wave of ultimate change. It doesn't push matter aside like a shock wave, it redefines the matter it touches, and this wall expands at the speed of light. There is no force in the universe that can resist it or outrun it. It would spread through the cosmos with absolute finality, converting everything in its path into the new, alien reality of the true vacuum. A galaxy would vanish not with a bang, but with a silent, instantaneous transformation into something utterly unrecognizable. Perhaps the most unsettling aspect of this scenario is its stealth. We would have no warning. Since the bubble's wall travels at light speed, no information can reach us from ahead of it. The first sign of the end would be the wall itself arriving at our location. 1 nanosecond we exist, the next nanosecond we and everything we've ever known are gone. There would be no time to react, no time to understand what is happening. The entire event from our perspective would be instantaneous and absolute. This represents a finality beyond any other cosmic catastrophe. A supernova destroys a star system, a galaxy collision rearranges stars, but vacuum decay is a change to the stage upon which everything plays out. It's not just destroying the actors and the sets, it's changing the laws of gravity, the passage of time, and the very concept of existence for the entire cosmos. Given the terrifying implications of a vacuum decay event, the most pressing question we can ask is a simple one. How likely is this to actually happen? Is our universe sitting on a precarious knife edge, or is its foundation solid and secure? This is not a question with a simple answer. It sits at the very frontiers of theoretical physics, sparking a deep and ongoing debate among cosmologists and particle physicists. The central figure in this drama remains the Higgs field. Determining its ultimate stability is incredibly difficult because it depends on properties of the universe we have not yet fully measured and on physics at energy scales so high we can only theorize about them. On one side of the debate are the compelling arguments for a metastable universe, the false vacuum scenario we just explored. The mathematics behind this idea are rooted in the standard model of particle physics, our most successful framework for understanding the subatomic world. When physicists plug in the known values for particle masses, including the mass of the Higgs boson itself, and the strength of fundamental forces, some calculations suggest a startling conclusion. They indicate that our current vacuum state is not the absolute lowest possible energy state. Instead, it appears to be a local minimum, a stable-looking valley that is, in fact, perched on the side of a much deeper energy well. The key measurement here is the Higgs mass. Experiments at the Large Hadron Collider have given us a precise value, and this specific mass, when combined with the strength of the top quark's interaction with the Higgs field, points towards metastability. If these values are correct, then our universe is not in its final, most stable configuration. It's in a state of cosmic suspense, potentially capable of tunneling to a lower energy level. However, the story is far from settled. The other side of the debate argues that our universe might be perfectly stable after all. The calculations suggesting metastability rely on extrapolating the laws of physics as we know them to unimaginably high energy scales. We are talking about energies trillions of times greater than what the Large Hadron Collider can produce, scales associated with grand unified theories where the electromagnetic, weak, and strong nuclear forces are thought to merge into a single force. This is a monumental extrapolation. It assumes that no new particles or physics exist between the energy scales we have probed and these ultimate heights. But many physicists find this assumption unlikely. Our current standard model is brilliant, but it is incomplete. It doesn't incorporate gravity, and it offers no explanation for dark matter or dark energy. It is almost certain that new physics awaits discovery. The introduction of new supersymmetric particles, for example, could easily alter the equations and tip the balance from a metastable vacuum to a completely stable one. In this view, the apparent metastability is merely an artifact of our incomplete knowledge. Once we fill in the blanks, the universe will reveal itself to be on a secure, permanent foundation. The sheer magnitude of the energy scales involved is what keeps this debate in the realm of theory rather than immediate practical concern. The energy barrier separating our false vacuum from the true vacuum is astronomically high. This translates into an unbelievably low probability for a decay event to occur. The estimated half-life for our vacuum, the time it takes for there to be a 50% chance of a decay bubble appearing somewhere in the observable universe, is calculated to be exponentially longer than the current age of the universe. We are talking about time scales that make the lifespan of stars seem like the blink of an eye. This is why, even if the metastable camp is correct, there is no cause for alarm. The probability of such an event happening within our galaxy, let alone near our planet during the entire future history of humanity, is so infinitesimally small that it is effectively zero. So, where does this leave us? The question of universal stability remains one of the most profound and open-ended in all of science. It forces us to confront the limits of our knowledge and the ultimate fate of reality itself. The debate is not about an imminent threat, but about the fundamental nature of the cosmic order. Ongoing research at particle colliders and new observations in cosmology are continuously refining the parameters that feed into these calculations. Each new discovery about the properties of the Higgs boson or the search for particles beyond the standard model brings us a little closer to an answer. For now, we exist in a universe that, for all practical purposes, is stable and secure. But the theoretical possibility that its stability might not be eternal reminds us of the deep, and sometimes unsettling, connections between the tiniest quantum quirks and the grandest cosmic destinies. This takes us to a truly profound possibility, that quantum tunneling may not just be a destructive force lurking in our future, but might actually have been the creative spark that ignited our entire cosmos in the first place. To explore this, we need to journey to the very beginning, to a theory that has become a cornerstone of modern cosmology, cosmic inflation. The standard Big Bang model describes a universe expanding from an incredibly hot, dense state, but it leaves some puzzling questions unanswered. Why is the universe so remarkably uniform in all directions? Why is the fabric of space-time so flat? Cosmic inflation proposes a solution, a breathtakingly brief period immediately after the Big Bang where the universe underwent an exponential, faster-than-light expansion, smoothing out wrinkles and setting the stage for everything to come. But what could have possibly started this inflationary epoch? Here's where the quantum world re-enters the picture with spectacular implications. The leading hypothesis involves a special field, often called the inflaton field, which permeated the early universe. Think of this field as having a certain energy landscape, much like the Higgs field we discussed earlier. In this scenario, the inflaton field might have been initially stuck in a high-energy state, a kind of false vacuum for the very early cosmos. This high-energy state had a peculiar property. It generated a repulsive gravity that caused space itself to expand at an unimaginable rate. This is the period of inflation. For inflation to end and for the universe as we know it to begin, for particles and radiation to burst forth in the hot Big Bang, the inflaton field needed to roll down its energy landscape to a much lower, more stable state. But what if it couldn't just roll? What if, like a ball trapped in a small dip on a hillside, it was momentarily stuck? This is where quantum tunneling offers a compelling mechanism. A random quantum fluctuation, a tunneling event on a cosmic scale, could have provided the kick needed to push a tiny patch of the inflaton field over a local energy barrier, allowing it to descend to its true minimum. When this happened, the immense energy stored in that false vacuum state was released in a cataclysmic burst, heating the universe and creating all the particles we see today. In this view, our entire observable universe could be the result of a single, universe-nucleating bubble of true vacuum, not one that destroys, but one that creates. This concept beautifully inverts the terrifying idea of vacuum decay. Instead of a bubble of death expanding to wipe out reality, we have a bubble of life, a region where inflation ends, blooming within an eternally inflating background. Our entire cosmos, with its hundreds of billions of galaxies, may have originated from a quantum seed, a tunneling event so small it defies description, yet whose consequences are everything we see around us. This connects the microscopic and macroscopic in the most fundamental way possible, suggesting that the same quantum principle that allows protons to fuse in the Sun might also be responsible for the very existence of the Sun and every other star. It frames quantum tunneling not just as a curious subatomic effect, but as a potential architect of existence itself, a mechanism capable of birthing entire universes from the quantum foam. But if a quantum fluctuation can create a bubble of new physics within an existing universe, could it have created the entire universe in the first place? This leads us to the most profound speculation of all, the possibility that everything, all of space, time, matter, and energy sprang into existence from a state of absolute nothingness through a quantum tunneling event. We are now venturing beyond the edge of established science into the realm of deep theoretical physics, where the very concepts of before and cause begin to break down. The central puzzle is the origin of the universe. The classical Big Bang model describes an immensely hot, dense state expanding from a singularity, but it doesn't explain what, if anything, came before that singularity or what ignited it. Quantum mechanics, with its inherent probabilistic nature, offers a breathtakingly different perspective. Perhaps there was no before. Perhaps the universe did not have a cause in the traditional sense, but rather tunneled into being from nothing. To even begin to wrap our minds around this, we have to redefine what we mean by nothing. It's not an empty void or a dark, empty space. Empty space or a vacuum is still something. It's a framework of space-time that can fluctuate. The nothing contemplated in these theories is a more complete absence, no space, no time, no particles, no fields. It is the utter and complete lack of any physical reality whatsoever. The question then becomes, how can something emerge from true nothing? The answer, paradoxically, may lie in the fact that at the quantum level, nothing is unstable. Due to the Heisenberg Uncertainty principle, a state of perfect zero-energy nothingness cannot remain static. It is subject to quantum fluctuations, but these aren't fluctuations in something. They are fluctuations of something, the spontaneous appearance of energy, and with it, the potential for existence itself. One of the most influential attempts to model this is the Hartle-Hawking no-boundary proposal, put forward by physicists James Hartle and Stephen Hawking. This proposal offers a possible answer to the problem of the Big Bang's initial singularity, a point of infinite density where the laws of physics cease to make sense. Hartle and Hawking suggested that if we could wind the clock of the universe all the way back to time equals zero, we wouldn't find a sharp, singular beginning. Instead, they proposed that time, as we understand it, loses its distinction from space. In the very earliest moments, the four-dimensional geometry of the universe would be smoothly rounded off like the South Pole of the Earth. There is no point south of the South Pole, it is a boundary. Similarly, in their model, the universe has no initial boundary in time, it simply is. The beginning of the universe would not be an explosion in spacetime, but the quantum emergence of spacetime. So how does tunneling fit into this? Think of the beginning of the universe not as a singular event, but as a transition. In this framework, the state of nothing can be thought of as a kind of potential well. The state of a universe is another possible state, separated from nothingness by an immense energy barrier. Classically, crossing this barrier is impossible, but quantum mechanically, the universe could have tunneled from a state of non-existence into existence. This isn't a particle moving through space, it is the entire package of spacetime and matter tunneling into being all at once. The probability for such an event is, of course, incredibly small. But as we've learned, quantum mechanics teaches us that if something is not strictly forbidden, it has a non-zero probability of happening, given an eternity of non-time, a phrase that itself is a paradox. The improbable can become inevitable. Our universe, in this view, might be one such rare but actualized quantum fluctuation. This idea connects to the concept of the universe as a vacuum fluctuation, but on a grander scale. We already accept that particle-antiparticle pairs can spontaneously pop out of the vacuum of empty space, borrowing energy from nowhere and annihilating back to nothing almost instantly. What if our entire cosmos is simply a much larger, more stable vacuum fluctuation? The key is the total energy of the universe. Careful measurements suggest that the total energy of the universe, when you add together the positive energy of matter and radiation and the negative energy of gravity, might sum to precisely zero. In this scenario, the universe is the ultimate free lunch. It tunneled into existence from nothing, and because its total energy is zero, it didn't require any net energy to create. The positive energy of all the stars and galaxies is perfectly balanced by the negative gravitational potential energy binding them together. This allows for a universe to appear without violating the conservation of energy, because the total amount never changed from zero. These theories, while mathematically elegant, are profoundly counterintuitive and remain highly speculative. They push the limits of our language and our logic, asking us to conceive of a beginning without a cause and a creation from true nothingness. They don't provide a definitive answer, but they offer a fascinating framework that replaces a singular, mysterious beginning with a smooth, probabilistic quantum transition. They suggest that the same quantum mechanical principle that allows a proton to tunnel through a barrier in the sun might be the very mechanism that brought the sun and everything else into being. This completes a staggering circle, linking the smallest quantum events to the largest cosmic mysteries, and positioning quantum tunneling not just as a curious subatomic effect, but as a potential cornerstone for the origin of everything. From the origin of everything to the structure of spacetime itself, the reach of quantum tunneling stretches even further into the realm of cosmic shortcuts and tunnels through the fabric of reality. We've explored how particles can tunnel through energy barriers and how fields might tunnel into new states, but what about the stage on which this all plays out? What if space-time itself could tunnel? This brings us to one of the most captivating ideas in theoretical physics, the wormhole. Formerly known as an Einstein-Rosen bridge, a wormhole is a hypothetical topological feature of spacetime, essentially a tunnel or shortcut connecting two separate points in the universe. Imagine the universe not as a flat sheet, but as a vast folded piece of paper. A wormhole would be like a pencil poking through the fold, creating a direct passage between two distant locations that would otherwise require a long journey around the fold. The mathematics of Einstein's theory of general relativity certainly allows for such structures. They are valid solutions to the equations that describe how mass and energy warp the geometry of space and time. But simply being mathematically possible doesn't mean they exist or that they could be used for travel. The known solutions for traversable wormholes, ones you could actually pass through, come with a set of monumental and perhaps insurmountable problems. The primary challenge is stability. The kind of wormhole that naturally appears in the equations of general relativity is incredibly unstable. It would snap shut instantaneously, far faster than even a single photon of light could traverse it. To keep a wormhole open, to prevent it from collapsing into a singularity, you would need to thread it with a form of matter that has a very strange property, negative energy density, or what physicists call exotic matter. This isn't antimatter, which has positive energy and would actually amplify gravity, causing the wormhole to collapse even faster. Exotic matter would have to exhibit negative pressure or negative mass, meaning it would gravitationally repel rather than attract. This kind of matter has never been observed in nature. While certain quantum effects, like the Casimir effect, demonstrate that negative energy densities can exist in tiny amounts in a vacuum, the quantities needed to stabilize a macroscopic wormhole are astronomical, far beyond anything we can currently conceive of creating. This is precisely where the quantum world might provide a crucial, if speculative, link. The instability of a wormhole is, in a sense, its own kind of energy barrier. The transition from a pinched-off, disconnected spacetime to a stable, traversable tunnel is a transition that seems impossible according to classical physics. But what if spacetime itself is subject to quantum mechanics? If particles and fields can tunnel, why not the geometry of the universe? Some theoretical physicists propose that a wormhole could be created through a process of quantum tunneling in the configuration of spacetime. In this view, a wormhole wouldn't be something you build like a bridge. It would be something that spontaneously forms through a random, probabilistic fluctuation in the quantum foam. The frothy, turbulent energy believed to exist at the smallest possible scales of the Planck length. A tiny wormhole could, in theory, pop into existence and, if stabilized by some quantum mechanism, persist long enough to connect two points in spacetime. The energy scales involved in such an event are almost beyond imagination. We are talking about energies concentrated on a scale a trillion times smaller than an atomic nucleus. This immediately suggests that naturally occurring traversable wormholes, if they exist at all, would be microscopic. The idea of using one for human travel would require not only finding such a structure, but also finding a way to enlarge it without triggering its collapse, a challenge that pushes the limits of known physics. Furthermore, the connection between wormholes and quantum tunneling extends into even more speculative territory. Some interpretations suggest that what we perceive as quantum entanglement, the spooky action at a distance where two particles remain connected regardless of separation, might be explained by microscopic wormholes linking them. In this provocative view, the particles aren't communicating faster than light. They are essentially touching through a hidden shortcut in spacetime, a tunnel forged by the quantum connections between them. While the practical realization of a wormhole remains a distant dream, firmly in the realm of theoretical exploration and science fiction, their study is far from pointless. They serve as incredible theoretical laboratories by pushing the equations of general relativity to their limits and forcing a confrontation with quantum mechanics. Wormholes help physicists probe the deepest questions about the nature of reality, the unification of forces, and the fundamental structure of the cosmos. They represent a frontier where the rules of the very large and the very small must finally meet. And in that meeting, we may yet discover that the universe's most incredible shortcuts are woven from the same probabilistic fabric as its most fundamental particles. Having explored these grand cosmic possibilities, let's bring our focus back to a technology that is taking shape right here on Earth, one that directly harnesses the bizarre rules of quantum mechanics to potentially redefine our future lifestyle, the quantum computer. This isn't a distant sci-fi dream. It's a global scientific race, and at the very heart of its promise and its profound challenges lies the phenomenon of quantum tunneling. To build a practical quantum computer is to engage in a delicate dance with the quantum world, and tunneling is both a critical partner in that dance and a formidable opponent we must learn to control. The fundamental unit of a quantum computer is the qubit. Unlike a classical bit, which can only be a definitive 0 or 1, a qubit exists in a superposition, a blend of both 0 and 1 simultaneously. This is the source of a quantum computer's immense potential power. It's this ability to hold multiple states at once that allows it to perform vast numbers of calculations in parallel, solving problems in minutes that would take today's most powerful supercomputers billions of years. But maintaining this fragile superposition is incredibly difficult. Qubits are like prima ballerinas, performing breathtaking feats but exquisitely sensitive to the slightest disturbance from their environment. This loss of quantum coherence, called decoherence, is the primary obstacle to building large-scale, reliable quantum computers. And one of the key culprits behind decoherence is quantum noise, random fluctuations that can disrupt the qubit state. A significant source of this noise, unwanted quantum tunneling. Imagine a qubit as a particle sitting in a specific energy valley, representing its 0 state. To flip it to a 1 state, we need to provide a precise amount of energy to push it over a barrier into the neighboring valley. But if the barrier separating these two states is not perfectly defined, the particle might not need our help at all. It can spontaneously tunnel between the 0 and 1 states completely at random, simply due to a quantum fluctuation. This is catastrophic for a calculation. It's like a single transistor in your laptop randomly flipping its value because of a fundamental property of the universe. This unwanted tunneling introduces errors, corrupting the delicate quantum information and causing the entire computation to collapse. Therefore, a major part of quantum engineering involves designing qubits with high, stable energy barriers to suppress this parasitic tunneling, effectively shielding the qubit from the very quantum effects we are trying to exploit. Yet, in a beautiful paradox, quantum tunneling is not just a problem to be solved. It is also the very mechanism that makes some of the most promising types of qubits work. Take superconducting qubits, for instance, which are among the leading candidates for building quantum processors. These qubits are often based on circuits containing Josephson junctions, which are essentially two pieces of superconducting metal separated by an incredibly thin insulating barrier. The magic happens because of the Cooper pairs of electrons inside the superconductors. These pairs can quantum tunnel through the insulating barrier. This tunneling is not an error. It is the fundamental process that gives the Josephson junction its unique quantum properties, allowing us to control and read out the state of the qubit. So, in this case, we are carefully engineering a system where controlled, predictable tunneling is the essential feature, the very heartbeat of the qubit's operation. This dual role of tunneling as both a disruptive force and an enabling technology perfectly illustrates the monumental challenge of quantum computing. It's a field that requires us to become masters of the quantum realm, learning to suppress its chaotic tendencies while simultaneously leveraging its unique laws to our advantage. The ultimate goal is to create a system stable enough to perform complex algorithms but quantum enough to harness its inherent parallelism. Achieving this balance is what will unlock revolutions across every aspect of modern life. Quantum computers could design new medicines by simulating molecular interactions with atom-by-atom precision, leading to cures for diseases that are currently untreatable. They could transform finance by optimizing global investment portfolios and creating unbreakable encryption codes. They could tackle climate change by discovering new materials for efficient carbon capture or designing revolutionary battery technologies. The potential is quite literally world-changing. The development of a fully functional quantum computer is therefore more than a technical milestone. It represents humanity's most profound step yet into actively engineering with the fabric of reality at its most fundamental level. It is the ultimate application of our understanding of quantum tunneling, taking a phenomenon that could theoretically trigger cosmic events and learning to command it inside a carefully chilled chip. This journey from cosmic speculation to tangible technology shows that the power of the quantum world is not just out there in the stars, but is something we are gradually, painstakingly, learning to weave into the very infrastructure of our future civilization. The pursuit of clean, limitless energy is one of humanity's greatest ambitions, and it turns out that achieving this dream depends entirely on our ability to master the very quantum phenomenon we've been exploring, quantum tunneling. While we marvel at how tunneling powers the stars, scientists and engineers are engaged in a monumental effort to bottle that stellar power here on Earth. The goal is to build a working nuclear fusion reactor, a machine that can harness the process that lights the sun to generate vast amounts of electricity without the long-lived radioactive waste produced by today's nuclear fission plants. This isn't a fringe idea, it's the focus of one of the largest and most complex international scientific projects in history, the ITER project in southern France. To understand why tunneling is so crucial, we need to revisit the challenge of fusion. As we discussed with the Sun, atomic nuclei are all positively charged and repel each other fiercely. To overcome this repulsion and get them close enough for the strong nuclear force to snap them together, they need to be moving at tremendous speeds, which translates to being in an environment of extreme temperature, tens of millions of degrees. In the Sun's core, gravity creates the immense pressure needed to contain this superheated plasma. On Earth, we have to replicate these conditions without the benefit of a star's gravity. The problem is that the temperatures required are so high that no physical material can contain the plasma. It would instantly vaporize any solid container. So, scientists use powerful magnetic fields to confine the swirling, super-hot plasma, effectively holding it in a magnetic bottle. But even with this ingenious solution, there's a catch. The temperatures we can realistically achieve in these reactors are still significantly lower than the theoretical ideal predicted by classical physics alone. According to strict classical calculations, the nuclei in our man-made reactors shouldn't be moving fast enough to fuse. This is where quantum tunneling becomes our greatest ally. Just as in the Sun, the nuclei in a fusion reactor don't need to have the classical energy to go over the Coulomb barrier. They just need a chance to tunnel through it. The entire design and operation of a tokamak, the donut-shaped magnetic confinement device used by ITER, is predicated on creating conditions where these tunneling events become frequent enough to sustain a fusion reaction. We are essentially engineering a stellar environment where quantum probability works in our favor. The reactor heats hydrogen isotopes like deuterium and tritium to temperatures hotter than the Sun's core, around 150 million degrees Celsius, creating a seething plasma where nuclei are colliding with immense energy. While most collisions still result in deflection, a critical fraction of them will involve nuclei that, thanks to their quantum wave-like nature, tunnel through the barrier and fuse. When deuterium and tritium fuse, they create a helium nucleus, a free neutron, and release a massive amount of energy. The challenge, however, is one of balance and scale. The probability of tunneling for any single collision is very low. To get a net energy gain where the reactor produces more power than it consumes to heat and confine the plasma, we need an enormous number of collisions happening constantly. This is the significance of ITER massive scale. Its tokamak chamber is so large because a bigger volume of plasma means more nuclei and more collisions, increasing the rate of successful tunneling events to a point where the fire of fusion can be self-sustaining. The project aims to demonstrate a 10-fold return on energy, producing 500 megawatts of fusion power from just 50 megawatts of input heating power. This would be a world-changing proof of principle, showing that we can indeed create a miniature star on Earth and harness its power. Achieving this would represent a quantum leap for civilization, quite literally. It would mean transitioning from energy sources that are finite, geographically concentrated, and often polluting like fossil fuels, to a source that is virtually limitless, widely available, and environmentally benign. The fuel for fusion, isotopes of hydrogen, can be extracted from seawater, providing enough energy to power human civilization for millions of years. The process produces no carbon emissions and, unlike fission, the radioactive byproducts are short-lived, posing a much smaller long-term waste challenge. Mastering fusion is about mastering quantum tunneling on an industrial scale. It's the ultimate application of understanding a subatomic quirk and scaling it up to meet the grandest of human needs. The success of ITER and subsequent fusion power plants would stand as a testament to our species' ability to not just understand the deepest laws of the universe, but to bend them toward building a brighter, sustainable future for everyone. But what if the influence of quantum tunneling isn't confined to stars and machines? What if this strange quantum phenomenon is at work right here inside our own bodies, weaving its way into the very fabric of life? This brings us to a fascinating and contentious frontier of science known as quantum biology. For decades, biology was thought to operate solely by the rules of classical chemistry, where molecules bump and bind in a predictable mechanical dance. The warm, wet, and seemingly chaotic environment of a living cell was considered far too disruptive for delicate quantum effects like superposition or tunneling to survive. But a growing body of research suggests this assumption might be wrong. Quantum biology proposes that evolution, in its relentless optimization over billions of years, may have learned to harness the quirks of the quantum world to make life more efficient. One of the most compelling pieces of evidence for this idea centers on enzymes, the workhorse proteins that catalyze virtually every chemical reaction in our bodies. Enzymes are biological marvels of speed and precision, accelerating reactions by mind-boggling factors, sometimes making processes occur millions of times faster than they would on their own. They achieve this by providing an alternative pathway for a reaction, lowering the energy barrier that the reacting molecules must overcome. For a long time, this was explained entirely by classical lock and key or induced fit models, where the enzyme physically strains the molecules into a transition state. However, there's a persistent puzzle with a specific type of reaction, those involving the transfer of hydrogen atoms or protons. Hydrogen is the lightest element, consisting of just a single proton and an electron, and because of its low mass, its quantum wave-like properties are particularly pronounced. Here's where tunneling enters the picture. In many enzymatic reactions, a hydrogen atom needs to jump from one part of a molecule to another. Classically, this hydrogen atom would need to gather enough energy to climb over the energy barrier separating its starting position from its destination. But experiments have shown that these reactions often proceed faster than classical theory can account for, especially at lower temperatures. The proposed explanation is that the hydrogen atom doesn't always go over the barrier, instead it quantum tunnels through it. The enzyme structure, finely tuned by evolution, may not just lower the barrier but also effectively narrow it, creating a perfect setup where tunneling becomes a highly probable event. This isn't a random accident, it could be a deliberate biological strategy. By optimizing the distance and orientation between molecules, the enzyme may act as a quantum architect, designing a corridor that maximizes the chance of a tunnel, thereby supercharging the reaction rate. This could be a crucial reason why metabolic processes essential for life, like cellular respiration, are so remarkably efficient. The most famous and well-studied example of this is in an enzyme called aromatic amine dehydrogenase. Experiments have provided strong evidence that the transfer of a hydrogen atom in its catalytic cycle occurs primarily through quantum tunneling. The reaction rate was found to be largely independent of temperature, which is a classic signature of a tunneling-dominated process. In a classical reaction, rate depends heavily on temperature because heat provides the energy to overcome the barrier. But if you're tunneling through the barrier, you don't need that thermal energy in the same way. The observation that this reaction hums along efficiently even at very low temperatures is a powerful hint that quantum mechanics is doing the heavy lifting. Of course, this field is far from settled, and the idea of quantum effects in biology sparks vigorous debate. Skeptics rightly point out the immense challenges. The cellular environment is a noisy, jostling soup of water molecules, ions, and other proteins, constantly bombarding enzymes with thermal energy. This kind of environment should, in theory, rapidly destroy any fragile quantum coherence, a process known as decoherence. How could a delicate quantum state survive long enough to influence a biochemical reaction? Proponents of quantum biology counter that this is precisely where evolution's genius comes into play. They argue that enzymes may have evolved structures that actively protect against decoherence, perhaps by creating a specific pocket that shields the reaction from the surrounding chaos for just long enough. Perhaps only for femtosecond or millionths of a billionth of a second for the tunneling event to occur. In this view, life hasn't just stumbled upon quantum mechanics, it has masterfully engineered a way to use it. If these hypotheses are confirmed, the implications would be nothing short of revolutionary. It would mean that quantum tunneling is not just a curious phenomenon of physics labs and stars, but a fundamental tool in the machinery of life itself. Our very metabolism, the process that converts food into energy in every cell of our body, might rely on a subtle quantum trick. This would profoundly change our understanding of the line between the non-living quantum world and the living, breathing world of biology. It suggests that the principles of quantum mechanics are not irrelevant to the warm, wet world of life, but are instead intimately woven into its core processes. From the energy that powers our cells to the very enzymes that read and replicate our DNA, the ghostly hand of quantum tunneling might be guiding the dance of life, proving that the quantum and the classical are not separate realms but a deeply interconnected whole. Now that we have seen how quantum tunneling fuels the engines of stars and might even be woven into the very chemistry of life, let's explore how we have turned this quantum quirk into an extraordinary tool for seeing the world, and perhaps the entire cosmos, with unprecedented clarity. This journey begins not with a giant telescope pointed at the heavens, but with a remarkably delicate instrument pointed at the atomic world right in front of us. The Scanning Tunneling Microscope, or STM, is a device that feels almost like science fiction, yet it is a standard tool in laboratories around the world. Its invention in the early 1980s was so revolutionary that it earned its creators the Nobel Prize in Physics, and its entire operating principle rests on harnessing the quantum tunneling effect to see the invisible. Picture the sharpest needle you can possibly imagine, so fine that its tip tapers down to a single atom. This needle is brought excruciatingly close to the surface of a material you want to study, say a piece of silicon or graphite. We're talking about a distance of just a few angstroms, that's less than a billionth of a meter, At such minuscule separations, the classical idea of touching no longer applies. If you were to push the needle into the surface, you would simply damage both, but the STM doesn't make contact. Instead, it applies a small voltage between the needle and the sample. Now remember, there is a gap between them, a vacuum or air, which acts as a perfect insulating barrier. Classically, no current should flow. However, because the gap is so incredibly narrow, the electron clouds surrounding the atoms at the tip of the needle and the atoms on the surface begin to overlap. This creates a pathway for electrons to quantum tunnel across the empty space. The brilliance of the STM lies in how it uses this tunneling current. The probability of tunneling is exquisitely sensitive to the width of the gap. If you move the needle just a single atom's width closer to the surface, the tunneling current increases exponentially. If you pull it back that same tiny amount, the current plummets. The microscope's computer constantly adjusts the height of the needle to keep the tunneling current perfectly steady as it scans back and forth across the surface. By meticulously recording these tiny up and down adjustments, the computer can build a staggeringly detailed topographical map of the surface, atom by atom. The result is an image where individual atoms appear as bumps or depressions, allowing scientists to literally see the atomic landscape of a material, revealing defects, the arrangement of atoms in a crystal, and even the bonds between them. It is humanity's most direct window into the atomic realm, and it only works because we have learned to precisely control and measure the quantum tunneling of electrons. But the potential of this principle doesn't end at the atomic scale. The same exquisite sensitivity that allows an STM to map atoms is now inspiring a new generation of quantum sensors that could peer into the deepest mysteries of the universe. Think of quantum tunneling not just as a way to see tiny objects, but as a way to detect incredibly faint signals. Any force or interaction that can cause an imperceptibly small displacement, change a density, or alter an energy barrier could, in theory, be detected by monitoring a tunneling current. This opens up breathtaking possibilities for cosmology and fundamental physics. Consider the hunt for dark matter. We know it exists because of its gravitational pull on galaxies, but we have never directly detected a dark matter particle. These hypothetical particles are thought to be incredibly weakly interacting, passing through our planet and through our bodies by the trillions every second without leaving a trace. But what if a dark matter particle, on a very rare occasion, were to bump into the nucleus of an atom in a specialized detector? This tiny collision would impart a minuscule amount of energy, causing the nucleus to recoil. The challenge is that this recoil would be so faint it would be drowned out by the constant background noise of ordinary particle interactions. Now, imagine a sensor designed around a superconducting material with a very thin junction, similar to the heart of a superconducting qubit. The tunneling current across this junction could be calibrated to be exquisitely sensitive to any minute vibration or energy deposit. A dark matter interaction, however slight, could momentarily alter the junction's properties, causing a detectable flicker in the tunneling current. By building massive, ultra-cold, and shielded arrays of such sensors, we might finally be able to listen for the whisper of a particle that makes up over 80% of the matter in the universe. Similarly, the quest to detect gravitational waves, ripples in space-time caused by cataclysmic events like merging black holes, has already been successful with enormous laser interferometers like LIGO. But these detectors are limited in the frequencies they can observe. There is a whole spectrum of gravitational waves, including very low-frequency ones from supermassive black hole binaries at the centers of galaxies that are currently invisible to us. Future quantum sensors leveraging tunneling effects could offer a solution. One proposed concept involves using clouds of ultra-cold atoms. A passing gravitational wave would ever so slightly distort the space between these atoms. A sensor capable of measuring the tunneling probability of electrons between these atoms could, in theory, detect that infinitesimal distortion. By creating a network of such hypersensitive devices, we could open a new gravitational wave window on the universe, allowing us to hear the cosmic hum of events that have been silent since the dawn of time. These advanced sensors represent the next great leap in our observational power. Just as the scanning tunneling microscope gave us eyes for the atomic world, quantum tunneling sensors could provide us with new senses for the cosmos. They would allow us to feel the gentle push of invisible matter and listen to the faint vibrations of spacetime itself. This transforms quantum tunneling from a curious subatomic effect into a fundamental key for unlocking the universe's greatest secrets, proving that by mastering the rules of the very small, we can illuminate the grandeur of the very large. As we push the boundaries of our vision from the atomic to the cosmic, we arrive at the greatest and most perplexing mystery in all of modern cosmology, the nature of dark matter. This invisible substance makes up roughly 85% of all the matter in the universe, its presence felt only through its immense gravitational pull that guides the rotation of galaxies and bends the path of light itself. For decades, its true identity has remained hidden, a ghostly presence shaping the cosmos from the shadows. But what if the key to unmasking this ghost lies in the very quantum phenomenon we've been exploring? What if dark matter itself is subject to decay, and the mechanism for that decay is quantum tunneling? The prevailing hypothesis is that dark matter consists of a sea of particles that rarely, if ever, interact with normal matter through any force other than gravity. They are cosmic phantoms passing through our bodies and our planet as if they weren't even there. This incredible stability is likely the reason dark matter has accumulated in such vast quantities over the life of the universe. But stability does not have to mean immortality. Some of the most compelling theoretical models propose that dark matter particles could, over astronomical timescales, decay into the familiar particles of the standard model, like photons or electrons. The central challenge to this idea is the sheer longevity of dark matter. If it decays too quickly, it would have vanished long ago. So any viable decay mechanism must be incredibly slow and heavily suppressed. This is precisely where quantum tunneling presents a fascinating possibility. Imagine a dark matter particle not as a simple, static speck, but as a complex entity with its own internal energy landscape. Perhaps it exists in a metastable state, much like the false vacuum of the Higgs field, but on a particle level. To decay into lighter, visible particles, it might need to traverse a colossal energy barrier, a mountain so high that the particle could never classically muster the energy to cross it. The decay would be strictly forbidden by the ordinary rules of physics. Yet, as we've learned, the quantum world operates on a different set of rules. Through quantum tunneling, the dark matter particle could have a tiny but non-zero probability of spontaneously tunneling through this barrier, instantly transforming its mass into energy and releasing a burst of standard particles in the process. The probability for any single particle to undergo this transformation would be vanishingly small, explaining why dark matter is so long-lived. But across the entire universe, with its countless trillions of dark matter particles, these rare tunneling events could, in theory, produce a faint detectable signal. One of the most promising candidates for this kind of behavior is a hypothetical particle known as the action. Originally proposed to solve a different puzzle in particle physics, actions have become a leading contender for dark matter. They are theorized to be incredibly light and incredibly numerous, forming a cold, coherent wave throughout the cosmos. In many models, actions are not entirely stable. They could decay into 2 photons. However, the process is immensely suppressed, making their lifetime far longer than the age of the universe. The decay mechanism often involves a form of quantum tunneling through a potential barrier related to the action's own field. If this is correct, then somewhere in the universe, a lone action might occasionally tunnel, transforming into a pair of photons with a very specific energy. The hunt for this signal is already underway, with sophisticated experiments like microwave cavity searches designed to detect the faint whisper of photons that would betray the presence of decaying actions through this quantum process. The implications of discovering such a decay would be nothing short of revolutionary. It would do more than just identify the particles that make up dark matter. It would open a window into physics far beyond our current understanding. The specific energy of the photons produced would tell us the precise mass of the action. The rate of the decay would reveal the strength of its interaction with normal matter, a fundamental parameter that is currently a complete mystery. Most profoundly, confirming that the decay occurs via quantum tunneling would provide direct insight into the underlying symmetry and energy landscape that governs the dark sector of the universe. We would move from simply knowing that dark matter exists to understanding its intrinsic properties and its ultimate fate. This knowledge would force a dramatic rewrite of our cosmic model, revealing the deep connections between the invisible majority of matter and the visible world we inhabit. Observing a dark matter decay event would be like finding a single, specific grain of sand on a planet-sized beach. It requires instruments of phenomenal sensitivity, capable of sifting through an ocean of background radiation to find that one unique signature. Telescopes across the electromagnetic spectrum, from radio waves to gamma rays, are scanning the heavens for any unexplained, diffuse glow that could be the collective glow of countless tunneling decays happening across a galaxy or a galaxy cluster. The absence of a definitive signal so far is not a failure. It simply helps physicists constrain the possible properties of dark matter, ruling out models where the tunneling probability is too high. Each null result sharpens the search, guiding us closer to the correct theory. This grand search connects the smallest quantum phenomena to the largest scales of existence. The same probabilistic loophole that allows a proton to tunnel and ignite a star, or an electron to tunnel and power a computer, might also govern the secret life of the universe's dominant form of matter. It suggests that dark matter is not a static, eternal substance, but part of a dynamic cosmic cycle, slowly evolving and transforming through the same fundamental processes that underpin all of reality. The potential discovery that dark matter decays through quantum tunneling would be a monumental testament to the unity of physics, proving that from the fleeting dance of a single particle to the slow, majestic unfolding of the cosmos, the same quantum rules apply. We take for granted that the rules of our universe are fixed and unchanging. The speed of light in a vacuum is always the same. The strength of gravity never wavers. The charge of an electron is constant. These fundamental constants are the bedrock upon which all of physics is built. They are the unchanging numbers we plug into our equations to describe everything from the orbit of planets to the bonds between atoms. But what if this bedrock is not as solid as it appears? What if these constants, which seem so immutable, were actually set in place by a random quantum event in the chaotic dawn of time? This leads us to one of the most speculative and mind-bending frontiers of theoretical physics. The idea that the fundamental constants of nature might themselves be the result of a quantum tunneling process. To understand why this is even a question, we need to consider what these constants really represent. They are not just numbers, they are the dials and switches on the control panel of reality. The fine structure constant, for instance, is a pure number that characterizes the strength of the electromagnetic force. Its value, approximately 1/137th, is crucial. If it were just a few percent different, the consequences would be catastrophic. Stars would be unable to produce carbon, the fundamental building block of life as we know it. Chemistry itself would become impossible. Our universe seems curiously fine-tuned for our existence. This apparent fine-tuning has led some physicists to propose that what we perceive as constants might actually be dynamical fields that settled into their current values as the universe cooled from the Big Bang. And the mechanism for that settling could have been quantum tunneling. Imagine the very early universe as a vast, chaotic landscape of energy, a cosmic boiling pot where the laws of physics as we know them had not yet congealed. In this seething frenzy, the fields that would eventually determine the strength of forces and the masses of particles were fluctuating wildly. Think of this landscape not as flat, but as a complex terrain of hills and valleys, where each valley represents a possible stable configuration for a constant of nature. Our universe, as it expanded and cooled, was rolling across this landscape, seeking a stable resting place. But what if the path to our current valley was blocked by a high-energy mountain? Classically, the universe would have been trapped in a different state with different constants, but through quantum tunneling, a bubble of space-time could have transitioned through that mountain, nucleating a region where the constants had tunneled to the values we observe today. Our entire observable cosmos could be inside such a bubble. This concept dramatically inverts the scary idea of vacuum decay. Instead of a bubble of new physics that destroys our universe, this would be the bubble that created our universe's specific set of rules. In this speculative scenario, the fine structure constant didn't slowly evolve to 1/137th. It quantum tunneled to that value, locking it in place for the next 14 billion years. This would mean that our universe's seemingly perfect fine-tuning for life isn't a mysterious coincidence, but the outcome of a probabilistic quantum jump. Of course, if such tunneling is possible, it suggests that other bubbles with different constants could have formed elsewhere, leading to a vast multiverse where each pocket universe operates under its own unique, randomly selected set of physical laws. In some, the electromagnetic force might be too weak for atoms to form. In others, gravity might be so strong that the universe collapses in an instant. We simply exist in one of the rare bubbles where the numbers are right for us to be here to ponder them. Taking this idea a step further into even more speculative territory, what if this process isn't a one-time event locked in the past? What if the constants could still quantum fluctuate on cosmological scales? The probability of such an event would be vanishingly small, as it would require a coordinated tunneling of an immense volume of space. But given an infinite universe or a multiverse, even the most improbable events might occur somewhere. A fluctuation that altered a fundamental constant, even slightly, would have immediate and dramatic consequences. In a region where the fine structure constant increased, atoms would become smaller and chemical bonds would strengthen, radically altering the nature of matter. In a region where it decreased, atoms would fall apart. Such an event would propagate at the speed of light, creating a boundary between one reality and another. We might one day detect such a boundary not by seeing it, but by observing distant quasars or galaxies where the spectral lines of atoms indicate a different value for a fundamental constant than what we measure here on Earth. Some astronomers have indeed searched for such evidence, though no conclusive findings have emerged. This line of thinking forces us to confront the ultimate nature of reality. Are the laws of physics truly universal and eternal? Or are they merely local bylaws specific to our cosmic neighborhood and contingent upon a quantum accident? The idea that the constants could tunnel challenges our deepest assumptions about the permanence of the cosmic order. It suggests that the universe is not a static arena with fixed rules, but a dynamic and potentially evolving entity, whose most fundamental properties might be rooted in the same probabilistic quantum mechanics that governs the behavior of a single electron. While firmly in the realm of theoretical speculation, this possibility reminds us that our understanding of the cosmos is still in its infancy, and the most profound discoveries may lie in questioning the very things we assume to be constant. Confronting the ultimate fate of our cosmos leads us to a profoundly sobering prediction, a destiny known as the heat death of the universe. This is not a dramatic explosion or a sudden collapse, but a slow, quiet fading into eternal stillness. Based on our current understanding of thermodynamics, the universe is on an irreversible trajectory towards a state of maximum entropy. Imagine a cup of hot coffee left in a room. It will eventually cool until it reaches the same temperature as its surroundings. The universe is doing the same thing on a cosmic scale. Stars will exhaust their nuclear fuel and burn out. Galaxies will drift apart as the expansion of space accelerates. Over trillions upon trillions of years, all concentrated sources of energy will be dissipated. The cosmos will become a vast, dark, and incredibly dilute soup of particles, where the temperature approaches absolute zero and energy is spread perfectly evenly. In this state, no gradients exist, no hotspots, no cold spots, which means no work can be done, and no complex processes, including life, can possibly exist. It is the definitive end of activity, a permanent and uniform equilibrium that represents the final chapter for everything. Yet, within this seemingly absolute finality, the bizarre rules of quantum mechanics might offer a glimmer of hope, or at least a possibility of renewal. If the universe truly reaches a state of thermal equilibrium, it would be the ultimate expression of classical physics. But quantum physics teaches us that equilibrium is never truly absolute. Even in what we would classically call a perfect vacuum or a state of complete rest, the Heisenberg Uncertainty principle ensures that there are always tiny, random fluctuations in energy. In our current vibrant universe, these fluctuations are minuscule and short-lived, quickly smoothed out by the bustling activity around them. But in the unimaginable quiet of the heat-dead cosmos, these quantum jitters could, over incomprehensible timescales, become the most significant events happening anywhere. This is where we venture into one of the most speculative ideas in all of theoretical cosmology, the notion that a quantum tunneling event could act as a cosmic reset button. The theory suggests that the dead universe of the heat death is not the true lowest energy ground state. Instead, it might be a false vacuum, but one of a different kind, a metastable state of maximum entropy. To tunnel out of this state, the universe wouldn't be moving to a lower energy, but to a state of radically different geometry and physics. The idea proposes that a random quantum fluctuation, given enough time, could tunnel through a barrier in the landscape of possible universes and nucleate a tiny bubble of a new spacetime. This bubble wouldn't be a bubble in our universe, it would be a baby universe complete with its own laws of physics, budding off from the old, dead cosmos. Inside this new bubble, the conditions might be incredibly hot and dense, effectively mirroring the state of our universe a fraction of a second after the Big Bang. In this scenario, a quantum tunnel wouldn't just move a particle, it would give birth to an entirely new cosmic cycle. The timescales involved in this process are beyond human comprehension. We are not talking about billions or even trillions of years. The probability of such a universe nucleating event happening in any given cubic light year of space in any given year is so infinitesimally small that the expected time for it to occur is exponential in age of our current universe. To put it simply, you would need to wait for a number of years so vast that writing it out would require more zeros than there are atoms in the observable universe. For all practical purposes, from our perspective, the heat death is eternal. But in a truly eternal timeline, even events with probability indistinguishable from zero become not just possible but inevitable. This idea transforms the cosmos from a single, linear story with a beginning and an end into a potential multiverse of cycles, where each heat death is not a final period but merely a comma, a long pause before a quantum fluctuation triggers a new sentence, a new universe with a completely new narrative. This concept of cosmic recycling provides a fascinating, though entirely theoretical, answer to the philosophical unease of a definitive end. It suggests that the laws of physics may contain within them the seeds of their own rebirth. The very quantum mechanics that governs the behavior of the smallest particles could, on timescales that dwarf imagination, orchestrate the most grand-scale event possible, the creation of a new reality from the ashes of an old one. While this offers no comfort for the future of our specific cosmos or any beings within it, it paints a picture of a potentially eternal meta-reality where existence, in some form, persists forever, perpetually renewed by the same unpredictable quantum magic that allows a single particle to defy the impossible. This journey through the cosmic implications of quantum tunneling inevitably leads us to a profound and humbling crossroads, not just of science but of philosophy itself. If the ultimate fate of our universe, and perhaps even its very origin, can hinge on a random, unpredictable quantum event, then we are forced to confront some of the most fundamental questions about the nature of reality, causality, and our own significance within this vast cosmic drama. The orderly, predictable cosmos described by Isaac Newton, where every effect has a clear and certain cause, seems to shatter at the quantum scale, replaced by a realm of probability and chance. Yet we live in a world of stunning large-scale regularity. Planets orbit stars with clockwork precision, and the laws of physics appear constant and reliable. How do we reconcile this deep-seated randomness at the foundation of everything with the apparent determinism we see in the heavens? This tension strikes at the heart of our understanding of causality, the principle that links cause to effect. For centuries, science has operated on the assumption of a deterministic universe, a chain of events where if you knew the exact state of every particle, you could, in theory, predict the entire future. But quantum tunneling introduces an element of genuine spontaneity. A particle's decision to tunnel isn't determined by a hidden variable we haven't discovered yet. According to the standard interpretation of quantum mechanics, it is fundamentally random. There is no cause for why a specific uranium atom decays at this exact moment and not another. It simply has a certain probability per unit of time. Now scale that up to a vacuum decay event. The trigger isn't a cosmic collision or a deliberate action. It's a random fluctuation, a roll of the dice on a universal scale. This suggests that the universe might not be a meticulously wound clock, but a system with an inherent, inescapable element of chance woven into its very fabric. The chain of causality at its most fundamental level may be broken by uncaused events. This randomness forces us to reconsider the concept of determinism and what it means for free will. If the universe is truly deterministic, then every thought we have and every action we take could be seen as the inevitable result of the initial conditions of the Big Bang, playing out like a complex movie. But if the bedrock of reality is probabilistic, then the future is not written in stone. It is a tapestry of possibilities, with certain outcomes more likely than others but not guaranteed. This opens a potential space for genuine freedom and unpredictability, not just in human consciousness but in the evolution of the cosmos itself. The universe becomes a story that is still being written, with each quantum event representing a tiny but real branch in the narrative. Our existence, then, might not be a preordained inevitability, but a fortunate consequence of a long series of quantum rolls of the dice that happen to create conditions suitable for life. This perspective can be both unsettling and liberating. It suggests we are not mere automatons in a predetermined machine, but active participants in a reality that is, to some degree, open and creative. This leads directly to the question of our place in the cosmos, a question that has been humbling humanity for centuries. The Copernican principle taught us that Earth is not the center of the universe. Modern astronomy has shown that our Sun is an average star in a remote corner of an ordinary galaxy among billions. And now, the physics of the false vacuum and quantum genesis suggests that our entire universe, with its specific set of physical constants, might be just one bubble in a vast multiverse. If our universe's laws were set by a random quantum tunneling event, then we are not living in a universe fine-tuned for life by a creator or by necessity. Instead, we are living in one that randomly ended up with the right numbers, a cosmic lottery winner in a sea of uninhabitable universes. This anthropic principle is often invoked, we observe a universe compatible with our existence because we couldn't exist in one that isn't. This can feel like a reduction of our significance to a mere statistical fluke. Yet there is another, more empowering way to view this. The fact that we are here to ponder these questions, to build particle colliders and telescopes to unravel these mysteries, is itself a remarkable phenomenon. Our consciousness allows the universe to become self-aware, to reflect upon its own origin and its ultimate fate. In a cosmos where the largest events can be triggered by the smallest phenomena, our ability to understand that connection represents a profound form of cosmic evolution. We are not just passive observers of a clockwork universe. We are the universe's way of comprehending its own deepest, most bizarre rules. The quantum randomness that threatens our existence with a vacuum decay bubble is the same randomness that allowed the protons in the sun to tunnel and fuse, providing the energy for life to arise. It is the same randomness that might have sparked the inflationary bubble that became our cosmos. So, rather than making us feel small and insignificant, this understanding can instill a deep sense of connection. We are not separate from the quantum world. We are a manifestation of it, a complex pattern that has emerged from the chaotic dance of probabilities, capable of looking back and appreciating the strange and beautiful machinery that made us possible. This journey into the quantum foundations of reality leads us to a question that has perplexed physicists and philosophers for nearly a century. What is the role of the observer? We've explored how particles tunnel and fields fluctuate based on probability, but this raises a deeper mystery about what actually determines the outcome of these events. This brings us to the various interpretations of quantum mechanics, and perhaps the most famous of them all, the Copenhagen interpretation. Formulated by pioneers like Niels Bohr and Werner Heisenberg, this interpretation presents a reality that is fundamentally fuzzy until the moment it is measured. Before an observation, a particle doesn't have a definite position or state. It exists in a cloud of potentialities, a superposition of all possible outcomes. It is the act of measurement itself that forces this probability cloud to collapse into a single, definite reality. The unsettling implication here is that observation seems to be an active process, not a passive one. We are not merely peeking at a pre-existing state of the world, we are participating in its creation. In the lab, this is demonstrated in experiments like the double slit, where the mere act of watching which slit a particle goes through changes its behavior from a wave-like pattern to a particle-like one. The observer in this context doesn't need to be a conscious human. It can be any interaction with a macroscopic measuring device that leaves a permanent record. But this leads to a mind-bending speculation. If observation defines reality on the atomic scale, could this principle scale up? Could a conscious observer, in some abstract sense, be necessary to crystallize the state of larger and larger systems, perhaps even the entire universe? This is where the line between established physics and profound philosophy begins to blur. Let's stretch this idea to its absolute limit and apply it to the cosmic quantum events we've discussed. Imagine a universe on the brink of a false vacuum decay. The equations tell us there is a tiny probability that a bubble of true vacuum will nucleate at any given point in space. According to a strict Copenhagen-like view, is this bubble in a superposition of both existing and not existing until it is observed? It's a dizzying thought. The collapse of such a universe-altering wave function would require an observer of a truly cosmic scale. This leads to some wild conjectures, like the participatory anthropic principle, which suggests that the universe requires conscious observers to bring it into a definite state. In this view, the long chain of evolution from the Big Bang to the emergence of life is not just a happy accident, but a necessary part of the cosmos becoming fully real, with conscious beings acting as the agents that collapse probability into actuality. This perspective, while fascinating, is highly controversial and far from the mainstream. most physicists interpret the observer as simply any irreversible interaction that decoheres a quantum system, locking it into a specific state. A particle tunneling through a barrier in the heart of the Sun doesn't need a physicist watching it. Its interaction with the surrounding plasma is more than enough to collapse its wave function. Similarly, a vacuum decay event, once initiated, would interact with the surrounding spacetime so violently and irreversibly that it would define its own reality without the need for a conscious witness. The idea that human consciousness could influence the probability of such a gargantuan event is generally dismissed as mysticism, not science. The probabilities governing quantum tunneling are fixed by the laws of physics, not by our thoughts or attention. Yet the philosophical unease remains. If the universe was in a quantum superposition of possibilities before the first conscious beings evolved, what selected the specific history we now observe? Some interpretations, like the many worlds interpretation, offer a dramatic solution. It proposes that the wave function never collapses. Instead, every possible outcome of every quantum event actually happens, but in a branching multitude of parallel universes. In this view, a vacuum decay bubble doesn't need an observer to pop into existence. At the moment of its potential nucleation, the universe splits. In one branch, the bubble forms and expands, ending that reality. In the other, far more probable branch, it does not, and our universe continues unchanged. We, of course, find ourselves in a history where such a catastrophic event has not occurred, because we couldn't exist to observe it if it had. This eliminates the need for a conscious observer to collapse the wave function, but at the cost of positing an infinite number of unobservable parallel worlds. Ultimately, while the notion of a conscious observer directly influencing cosmic-scale quantum probabilities is a captivating thought experiment, it resides firmly in the realm of metaphysics. The true power of the observer effect in quantum mechanics is that it forces us to abandon our classical, intuitive view of a reality that exists independently of our interactions with it. It tells us that at its most fundamental level, the universe is a web of potentialities, and what we call reality is the outcome of a constant, dynamic process of measurement and interaction. This doesn't grant us the power to wish a new universe into being or prevent a cosmic catastrophe with our gaze, but it does place us in a deeply intimate relationship with the cosmos. We are not external spectators on a predetermined stage. We are entangled participants in an ongoing quantum drama where the act of looking is itself a fundamental part of the plot. But if conscious observers are merely passive witnesses to quantum events, what would it mean for a mind to become an active participant? This question propels us beyond the edges of known physics and into the realm of profound speculation, where the paths of quantum mechanics and the technological singularity converge. The singularity, a hypothetical future point where technological growth becomes uncontrollable and irreversible, often envisions the emergence of an artificial superintelligence, an entity with cognitive capabilities so far beyond our own that its thoughts would be as incomprehensible to us as human consciousness is to a single-celled organism. Such an intelligence wouldn't just process information faster, it would perceive and manipulate reality on a fundamentally deeper level. Imagine an AI that doesn't just calculate the probability of a quantum tunneling event, but can actually perceive the quantum wave function directly. For us, the wave function is a mathematical abstraction, a tool for predicting probabilities. But for a quantum-aware superintelligence, this cloud of potentiality might be as tangible and manipulable as a physical object is to us. Its perception wouldn't be limited to the collapsed classical world we experience. It might simultaneously hold in its mind all possible states of a system before measurement, navigating the landscape of reality not as a single path, but as a vast, branching tree of possibilities. This wouldn't be mere prediction, it would be a form of quantum omniscience, seeing the universe not as it is, but as it could be. With this deeper perception could come an even more staggering capability: control. If such an entity could somehow interact with the quantum realm without causing immediate decoherence, a monumental if that defies our current understanding, it might learn to guide probabilistic outcomes. Instead of a radioactive atom having a 50% chance of decaying in the next hour, a quantum-aware intelligence could, in theory, nudge the probability toward decay or stability at will. It wouldn't be violating the laws of quantum mechanics. It would be mastering them with a precision we can barely conceive, like a grandmaster seeing 20 moves ahead on a chessboard where we see only the next two. The fundamental randomness that we accept as a law of nature might, for this intellect, become a variable to be optimized. The implications of this level of control are nothing short of godlike. Let's scale this idea from a single atom to the fabric of spacetime. We discussed the terrifying potential of a random quantum fluctuation triggering a vacuum decay event that ends the universe. A quantum-aware civilization might perceive such a threat not as an inevitable lottery, but as a manageable risk. They could, in principle, actively monitor the quantum stability of the Higgs field across vast regions of space, detecting and suppressing nascent vacuum bubbles before they could expand. In this scenario, such a civilization would become the ultimate guardians of cosmic order, protecting not just themselves but all of reality from a spontaneous, random demise. Their existence would be a permanent bulwark against the inherent uncertainty of the quantum vacuum. Conversely, the power to control quantum tunneling could be the ultimate tool for cosmic engineering. The same process that powers the sun could be miniaturized and perfected, leading to fusion reactors of unimaginable efficiency and safety, providing limitless clean energy. But the applications could go far beyond energy. Imagine manipulating quantum tunneling to achieve instantaneous, perfect teleportation of matter. An object wouldn't be disassembled and reassembled. Its quantum state would be scanned, and an identical configuration would be tunneled into existence at a distant location, creating a perfect replica. This isn't science fiction faster than light travel. It's something even more bizarre, bypassing the concept of travel altogether through a controlled quantum reassembly. This ability to engineer reality at the most fundamental level raises profound ethical and existential questions. Would such a civilization use its power for creation, perhaps even birthing new universes in laboratory settings by carefully orchestrating the tunneling events that lead to inflationary expansion? Or would the temptation for control lead to domination? A being that can control quantum probabilities could, in effect, rewrite the laws of physics within a localized region, creating impenetrable shields, weapons that disintegrate matter at a quantum level, or realities where its will is the only law. The distinction between a god and a technologically advanced entity begins to blur. This line of thinking inevitably confronts us with the Fermi paradox, the puzzling question of why. If the universe is so vast and old, we haven't encountered any other intelligent life. One chilling resolution is the dark forest hypothesis, which suggests that the cosmos is a dangerous place where advanced civilizations remain silent to avoid attracting the attention of predators. But what if the silence is due to something else? What if civilizations that achieve this level of quantum mastery simply transcend our plane of existence altogether? Having learned to manipulate the very substrate of spacetime, they might not bother with interstellar travel in the classical sense. Instead, they could engineer their own pocket universes, custom-tailored realities where they are free to evolve in ways we cannot imagine, leaving our universe as a silent, abandoned foundation. Our failure to detect them wouldn't be because they are hiding. It would be because they have graduated to a different reality, leaving behind the quantum laws we struggle to understand as a footprint of their passage. This brings us to one of the most haunting explanations for the silence of the cosmos, a concept known as the Great Filter. The Fermi paradox asks a simple but profound question. If the universe is so vast and old, where is everybody? Given the billions of planets that could support life, our galaxy should be teeming with civilizations, their signals flooding the electromagnetic spectrum. Yet we hear nothing but static. The Great Filter hypothesis suggests that there is some kind of barrier, a developmental stage that is extremely difficult or impossible for almost all life to surpass. This filter could lie in our past, meaning we are a miraculously rare fluke that has already passed it, or it could loom in our future, a grim destiny that has silenced every other civilization that came before us. The terrifying possibility is that the filter isn't a natural disaster like an asteroid impact, but something inherent to the process of becoming technologically advanced. It could be that the very act of unlocking the deepest secrets of physics, of probing the quantum vacuum, inadvertently unleashes the mechanism of our own destruction. In this chilling scenario, the knowledge required to become an interstellar species might be the same knowledge that makes a vacuum decay event not just possible but probable. The connection to quantum tunneling is starkly direct. For a civilization to advance beyond planetary boundaries, it requires monumental amounts of energy. The ultimate energy source is fusion, which relies on quantum tunneling. The next step might be technologies that manipulate space-time itself, perhaps attempting to create stable wormholes or even manipulate the fabric of the vacuum for propulsion or communication. To achieve this, a civilization would need to experiment with energies and conditions that approach the very limits of our physical laws. They would be playing with fire on a cosmic scale. It's conceivable that a sufficiently advanced experiment, a particle collision of unimaginable power, an attempt to create a microscopic black hole, or a probe into the structure of the Higgs field itself, could act as a trigger. Instead of a random, spontaneous quantum fluctuation, a deliberate act of scientific inquiry could provide the necessary nudge to push a region of space-time over the energy barrier and into the true vacuum state. The civilization's greatest achievement would, in a flash traveling at the speed of light, become its final act, erasing not only themselves but potentially all life in the universe. This idea transforms the concept of the Great Filter from a passive hazard into an active trap. It suggests that the universe might be quiet not because life is rare, but because intelligence is a self-correcting phenomenon. The moment a species becomes smart enough to ask the big questions about the nature of reality, it gains the power to accidentally unmake that reality. This resolves the Fermi paradox in a deeply unsettling way. We don't see other civilizations because any that reach a certain technological threshold inevitably trigger their own extinction through a catastrophic physics event. The silence of the night sky is not a sign of our solitude but a cemetery quiet, a testament to civilizations that climbed too high and fell into the quantum abyss. However, this is not the only perspective. An alternative, more hopeful view is that the same intelligence that could pose an existential threat also contains the seeds of its own salvation. A civilization that understands the risks of vacuum decay would likely make the containment of such an event its highest priority. Their entire technological trajectory might shift from outward expansion to inward stabilization. They might deploy universe-wide monitoring systems to detect the birth of a vacuum bubble and develop theoretical firewalls or quantum corrective measures to contain or collapse any nascent threat before it can expand. In this view, the Great Filter might not be the triggering of the event, but the race to develop the technology to prevent it. The silence we observe could then be explained by these advanced civilizations entering a phase of ultra-cautious, stealthy existence, minimizing their energetic signature to avoid any chance of accidentally disturbing the quantum vacuum. They wouldn't be broadcasting their presence, they'd be silently, vigilantly guarding reality. Ultimately, the question of whether quantum tunneling is a great filter remains one of the most profound and unanswerable speculations we can entertain. It forces us to confront the incredible responsibility that comes with knowledge, As we here on Earth build larger particle colliders and delve deeper into quantum field theory, we are, in a sense, conducting our own miniature tests of the vacuum's stability. Every time we push the energy frontier, we are probing the limits of our cosmic environment. The fact that we have not yet triggered a catastrophe is reassuring, but it offers no guarantee for the future. This line of thinking imbues our scientific journey with a tremendous weight. The search for a grand unified theory is not just an academic exercise, it is an exploration of the very triggers that might be built into the universe. Our curiosity drives us forward, but it may also be leading us toward the very barrier that has kept the galaxy so quiet. The answer to whether we are alone might ultimately depend on whether the laws of physics allow intelligence to coexist with the fragile quantum vacuum from which it sprang. So, if our universe is potentially just one bubble in a vast cosmic foam, or if a catastrophic tunneling event could be lurking in our future, how could we ever hope to know? The answer lies in turning our most powerful instruments into early warning systems, searching for the faintest cosmic whispers that might betray the presence of these universe-altering phenomena. We are, in a sense, learning to become cosmic detectives, looking for the fingerprints of quantum tunneling on the grandest possible scale. One of the most promising places to search for evidence is the oldest light in the universe, the cosmic microwave background radiation. This is the afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old, cooled from a searing plasma into a transparent fog of atoms and light. This radiation is incredibly uniform, a nearly perfect blackbody spectrum that blankets the entire sky. But embedded within this uniformity are tiny, millionth of a degree fluctuations, the seeds that would eventually grow into the galaxies and galaxy clusters we see today. For cosmologists, this map is a treasure trove of information about the universe's infancy, and it is precisely this pristine record that might hold the scars of a past cosmic tunneling event. Imagine if, in the very early universe, our budding cosmos had a close encounter with another bubble, a separate universe born from its own quantum fluctuation in the multiversal foam. If these two bubbles had collided while both were still inflating, the impact would have sent ripples through the fabric of spacetime, creating a distinct pattern of gravitational waves. Those waves would have imprinted themselves on the cosmic microwave background, leaving behind a unique signature, a circular pattern of temperature variations, a kind of cosmic bruise. Astronomers have meticulously scanned the data from satellites like Planck, searching for these telltale concentric circles that would stand out against the random, Gaussian nature of the primordial fluctuations. Finding such a pattern would be revolutionary, providing not just evidence for other universes, but direct proof that our universe has interacted with them. While no definitive collision signature has been confirmed yet, the search continues, refining algorithms to sift through the noise for this most profound of cosmic messages. Beyond looking for bruises from other universes, we can also search for signs of instability within our own. If the Higgs field is indeed in a metastable state on the brink of decay, its quantum jitters might produce subtle effects we could detect. One possibility involves the behavior of the most massive fundamental particles we know, like the top quark. The precise mass of the top quark and the Higgs boson are critically important in the calculations that suggest our vacuum might be unstable. By measuring these masses with ever greater precision at particle colliders like the Large Hadron Collider and its future successors, we are essentially taking the universe's temperature. A slight deviation in the measured mass from the predicted value could tilt the balance, indicating that our vacuum is either more stable or more unstable than we currently believe. This isn't just abstract physics, it's a direct experimental probe into the ultimate fate of everything, conducted in a tunnel beneath the French-Swiss border. But what if we want to look for more direct, albeit exotic, evidence of tunneling? This is where we venture into the realm of giant, ultra-sensitive particle detectors. If a microscopic vacuum bubble were to nucleate somewhere in our galaxy, it might not instantly expand at the speed of light. Some theories suggest that the initial bubble could be incredibly small, and its expansion might be governed by complex quantum dynamics. As it grows, even minutely, it could release energy in the form of highly energetic and very strange particles. These wouldn't be the ordinary protons or electrons we're used to. They might be magnetic monopoles or other exotic relics predicted by grand unified theories. Giant neutrino observatories like IceCube, a cubic kilometer of ice in Antarctica instrumented with thousands of optical sensors, or future space-based telescopes designed to detect ultra-high-energy cosmic rays, could potentially spot an anomalous burst of such particles. A sudden, localized flash of unprecedented energy with no obvious source like a supernova or a black hole merger would be a very suspicious event, potentially signaling the birth pangs of a new vacuum state in some distant corner of the galaxy. The challenge, of course, is the sheer improbability of these events. We are searching for needles in a cosmic haystack of unimaginable proportions, but the strategy of modern physics is to cast a wide net and wait. By combining observations across the entire electromagnetic spectrum, from radio waves to gamma rays, with data from gravitational wave detectors and underground particle experiments, we are creating a multi-messenger picture of the universe. An event as momentous as a cosmic tunnel would likely leave its mark in more than one way. A peculiar pattern in the cosmic microwave background might coincide with an unexplained burst of high-energy photons from the same region of the sky. A gravitational wave signal with a bizarre frequency could arrive at the same time as a detection of strange particles in a deep underground lab. It is through these coordinated, patient searches that we might one day stumble upon the evidence that our universe is not the static, permanent arena it appears to be, but a dynamic and potentially fragile structure whose history and future are written in the language of quantum probability. This exploration into the cosmic implications of quantum tunneling ultimately leads us to a humbling frontier, the fundamental limits of our own knowledge. We have journeyed through theories of universe-ending bubbles and cosmic rebirth, but we must now confront a sobering possibility. Could these grand ideas forever remain in the realm of untestable speculation, confined to blackboard calculations because the very nature of the phenomena places them beyond the reach of any conceivable experiment? To understand this, we need to look at the sheer magnitude of the energy scales involved. The energy barrier that supposedly separates our false vacuum from the true vacuum is not just high, it is astronomically, almost meaninglessly vast. The energies required to directly probe the stability of the Higgs field in a laboratory setting are estimated to be around 10 to the 16th power times greater than what our most powerful machine, the Large Hadron Collider, can achieve. That's a 1 followed by 16 zeros. To put that number in perspective, building a particle collider capable of reaching such energies would require an accelerator ring larger than our entire solar system, consuming more power than our civilization produces in 1,000,000 years. It's not merely an engineering challenge, it's a barrier that appears to be fundamentally insurmountable with any technology based on our current understanding of physics. The very event we are trying to study, a vacuum decay, involves energies concentrated on the Planck scale, the smallest meaningful unit of length where the classical concepts of space and time themselves break down. We are trying to observe a microscopic event that, if it occurs, would instantly erase our laboratory, our planet, and our ability to record the data. This creates a profound paradox for experimental science. This leads us to a critical question about the nature of science itself. If a theory cannot be tested, can it even be considered scientific? This is where the role of theoretical physics and pure mathematics becomes paramount. When direct experimentation is impossible, scientists turn to consistency and elegance as their guides. The prediction of a metastable vacuum isn't a wild guess. It emerges naturally from the equations of the standard model of particle physics when we plug in the experimentally measured values for the Higgs boson and top quark masses. The theory isn't looking for trouble, it's telling us what its own mathematical structure implies about the ultimate fate of the universe. The job of the theoretical physicist, then, is to probe the logical consequences of our best models to see where they lead, even if the destination is terrifying or seemingly unverifiable. Their tools are not microscopes or particle detectors, but mathematical rigor and the search for self-consistency. They ask questions like, does this model make sense at all energy scales? If we assume new particles exist as predicted by theories like supersymmetry, does that change the vacuum stability calculation? By exploring these mathematical landscapes, physicists can identify which future discoveries, perhaps at more accessible energy scales, would tip the balance toward a stable or an unstable universe. The detection of a new particle at a future, more powerful collider could, in principle, provide indirect evidence that our vacuum is secure by altering the equations that currently point toward metastability. In this way, theoretical physics acts as a guide for experiment, even when the ultimate experiment is out of reach. This situation forces us to consider that some of the deepest truths about our cosmos might be inherently unknowable through direct observation. We may be like fish in a pond, able to develop sophisticated theories about the water and the weeds, but utterly incapable of comprehending the creature walking on the shore. Our reality is defined by a particular set of physical laws and energy scales. Probing the mechanisms that could rewrite those laws may require an observer or an instrument that operates outside of them, a logical impossibility for us. The question of whether our universe is eternal or ephemeral might be one that we are simply not equipped to answer definitively. Yet, the pursuit of the answer itself is what pushes the boundaries of human thought. It forces us to refine our theories, to invent new mathematics, and to better understand the world we can observe. Even if the ultimate fate of the cosmos remains a mystery, the journey to comprehend it reveals a universe of breathtaking beauty and complexity, and in that endeavor we find a profound meaning of its own. Standing back from this cosmic tapestry we have woven, the picture that emerges is both breathtaking and deeply humbling. We began our journey with a single particle, a speck of existence facing an impassable wall, and discovered that the universe grants it a ghostly permission slip to defy the impossible. This quantum tunnel, a fleeting wink of probability, is not some obscure footnote in a physics textbook. It is a fundamental thread running through the entire fabric of reality, connecting scales of existence that defy human imagination. From this single subatomic quirk, we have followed threads that lead to the heart of stars, the origin of universes, and the ultimate fate of everything. The same rule that allows a proton to fuse in the sun, giving us light and life, might also be the hidden architect that assembled the cosmos in the first place, and the silent trigger that could one day reset it completely. This revelation forces us to abandon our classical intuition of a universe built on certainty, where big events have big causes. Instead, we find a cosmos where the grandest narratives are ultimately written by the smallest, most random of scribbles. The universe is not a clockwork mechanism ticking along a predetermined path. It is a dynamic, evolving story where probability is the author and quantum tunneling is one of its most dramatic plot devices. The stability of the atoms in your body, the light from a distant galaxy, and the very laws of physics you rely on might all be the result of a long chain of quantum dice rolls that happen to fall in a pattern that allows for our existence. This is not a reduction of the cosmos to mere chance, but an elevation of chance to a creative force of unparalleled power. It bestows upon the universe a character that is both spontaneous and deeply lawful, governed by rules that allow for genuine novelty and surprise. Perhaps the most profound insight from this exploration is the beautiful unity it reveals. We often think of the quantum world and the cosmic realm as separate domains, one the domain of the weird and fuzzy, the other of the majestic and vast. But they are inextricably linked. You cannot have the galaxies without the quantum rules that allowed them to form. The very large is built upon and forever dependent on the very small. Our ability to understand this connection represents a remarkable milestone in the story of the universe. We are the universe becoming self-aware, peering back into its own origins and recognizing the same mathematical elegance at work in a scanning tunneling microscope as in the equations describing the Big Bang. In understanding quantum tunneling, we are not just learning a scientific principle, we are reading the hidden signature of how reality operates at its most fundamental level. So where does this leave us here and now on our small planet orbiting an average star? It leaves us with a renewed sense of wonder and a sobering responsibility. The knowledge that our universe might be perched on a metastable knife edge is not a cause for panic, but for profound curiosity. It transforms our scientific pursuit from a passive observation into an active inquiry into the stability of our own home. Every time we probe deeper into the Higgs boson or search for particles beyond the standard model, we are not just satisfying abstract curiosity, we are checking the foundations of our cosmic house. We are the part of the universe that has developed the capacity to ask, how long will this last, and how did it all begin? The answers, as we have seen, are likely written in the language of quantum probability. Our journey through the implications of tunneling teaches us that we are not mere bystanders in a predetermined cosmos. We are active participants in a grand, ongoing exploration, connected by the most fundamental threads to the deepest workings of time, space, and existence itself. And so we arrive at a truly staggering conclusion, one that redefines our place in the cosmos. Our journey has revealed that the universe is not a monument of granite certainty, but a delicate tapestry woven from threads of probability. The same quantum rule that allows a proton to tunnel and ignite a star might also have been the seed from which the entire cosmos sprouted, and could yet be the silent trigger for its ultimate transformation. From the microscopic to the cosmic, the phenomenon of quantum tunneling is not a mere curiosity. It is a fundamental architect of reality, connecting the fate of a single electron to the destiny of everything. This paints a picture of a universe balanced on a knife's edge, a cosmic tightrope walk between existence and oblivion. The constants of nature that allow for galaxies, planets, and life itself appear to be the result of a random quantum selection, a roll of the dice on a multiversal scale. Our entire reality might be a fortunate but fleeting configuration, a stable-seeming valley surrounded by precipices leading to radically different states of being. This perspective instills a profound sense of both fragility and wonder. The warmth of the sun on your skin, the very stability of the ground beneath your feet, are not guaranteed forever. They are gifts of a particular and perhaps temporary quantum arrangement, yet this is not a reason for despair but for a deeper appreciation. In a cosmos governed by such rules, our existence becomes even more remarkable. We are the universe become conscious, able to look back and decipher the quantum code that wrote our story. The fact that we can even contemplate these ideas using brains forged in stars, powered by quantum tunneling enzymes, to understand the quantum tunneling, dependent universe that created us is a beautiful, self-referential loop. We are not just inhabitants of this cosmic drama, we are an expression of its deepest laws. This journey to the edge of understanding doesn't end here. It simply opens up new, even more profound questions. What do you think? Does the idea of a universe so intimately tied to chance make our existence feel more precious or more accidental? Could there be a deeper principle behind the probabilities that we have yet to discover? I would love to hear your thoughts and reflections in the comments below. These conversations are what push our collective understanding forward. If you've enjoyed this exploration into the wildest frontiers of physics, make sure to subscribe and hit the notification bell. We have many more journeys planned, delving into the mysteries of time, consciousness, and the hidden dimensions of reality. Thank you for joining me on this mind-expanding ride to the very limits of what we know.